So last video we talked about how your kidney helps balance your electrolytes. In this video we're going to talk about how your kidneys help balance water. And then the next video we're going to talk about how your kidneys help balance acid and base. So your kidneys are really important for homeostasis. But for the purposes of this video, we're just going to talk about how it helps balance water, fluid in your body. So right, fluid balance. And your body is about 60% water. We're about 60% water. And if you break it down, where that water is found, about 2/3 of it is found inside of cells. Water is found inside of the cell. We call it intracellular. Intracellular. And that leaves about 1/3 outside of the cell. It could be the fluid. Here's your red blood cells. It could be the fluid in your vessels. We call that plasma. It could be in your interstitium. It doesn't really matter as long as it's outside of the cell. So I'll write extracellular. Extracellular. And again, if you want to be really specific, then you can break it up. About 75% is in the interstitium, or interstitial space. And then about 25% is in the plasma. But you should just know 1/3 is extracellular. Why is this important? If you give a patient 3 liters of water, where does that water distribute? Well, we said 2/3 is intracellular, so 2 liters would go inside cells, intracellular. And then 1 liter would go in your extracellular space, extracellular. All right, that's one way they like to ask that. And you might say, how do we actually know that 60% of our body is water? How do we ever come to that conclusion? And I would just say science, but that doesn't explain things very well. So the way we kind of measured the amount of fluid, water in our body, is that we had experiments where people ingested an isotope of water. An isotope of water with an extra hydrogen. We call this heavy water, or D2O. And by measuring that, we measured exactly, we have 60% of our body's water. So this measures our total body water. Well, then how did we find out that 2/3 was intracellular and 1/3 was extracellular? I mean, we can't measure every little bit of water inside every little cell. That's impossible. So we said, well, we can't measure intracellular, but we can measure extracellular. We can give things that aren't reabsorbed or can't be metabolized, and they just kind of float in our interstitial space. And if we measure that, then we can measure how much fluid is extracellular. And so extracellular fluid is measured by giving things that can't be absorbed. You already know something that can't be absorbed. We talked about it in pharmacology. That'd be mannitol. Mannitol. And by measuring that, we can measure extracellular space. And by doing math, by subtracting total body water from extracellular, we have our intracellular. So that's how we came about kind of figuring out, okay, our body's made up of this much water, and this much is intracellular, this much is extracellular. Have gotten questions on how they measure it, so just be aware of that. Something else you should know, they want you to know what are the predominant cations and anions in these compartments. In your intracellular, inside your cell, the predominant cation is going to be potassium. Can you understand why that is? Don't you have your sodium, potassium, ATP, ACE pumps? That's found in every cell, yeah? Pumps out sodium, takes in potassium. Takes in potassium, and that's why potassium is the most abundant cation. What's the most abundant anion? It'll be phosphate. Why is that? Every time you use this pump, you break down ATP and you release phosphate, and so that's why phosphate is the most important anion. What's the most important cation in your extracellular space? Look at the pump. We take potassium in and then we pump sodium out. And so we pump that sodium out outside of the cell. That's exactly where you're going to find it. Outside of the cell, extracellular space. So sodium is the most important. What's the most important anion? In your blood, especially in your plasma, you have these negatively charged anions. They're so abundant. In fact, I'll give you a hint, they're the most abundant protein we have. That'll be albumin. Albumin. The most commonly tested thing about fluid balance is a shift between the fluids. Yeah, in certain types of situations, you can lose fluid. How does your body respond to that? How does that change our balance? That's always tested, and like I said, they like to test physio with charts and graphs and all these complicated things, and this is no different. So there's going to be a lot of charts and graphs when it comes to fluid balance, and you have to be able to recognize that well. So let's see if we can demystify it a little bit. All fluid changes come from your extracellular space. That's right, all fluid changes start in your extracellular space. So if you lose fluid through urinating, through sweating, through diarrhea, it comes out of your extracellular space. That just makes sense. I mean, it can't come from your intracellular space. Your body doesn't take a pipette and like draw out water from each of your cells. No, so it has to come from your extracellular space. All right. Now, fluid changes from your extracellular space. All right, you just lose kind of fluid from your extracellular space. However, if you lose proteins or osmolarity or sodium or salts from your extracellular space, so all right, you have a ton of proteins here, if you have proteins here, but if you lose that through diarrhea, through vomiting, through stuff, then you lose that osmotic pressure. And osmosis plays a huge role in this. Osmosis plays a huge role in this. And so I'll write osmolarity changes in ECF can cause your ICF to shift. Let's see if we can do some examples. Hopefully it becomes a little bit more clear when I do some examples. So the graphs they like to show are gonna look just like this, where you have your ICF and your ECF. In the bottom, the x-axis is gonna be volume, and the y-axis is gonna be osmolarity. What happens if you just take in some more isotonic water? You always said that all fluid changes start in your ECF, so you're going to add more volume to your ECF. Is it going to change your osmolarity at all? Is it going to change your y-axis at all? No. This is isotonic, right? So it doesn't change your osmolarity. There's no osmotic shift. This is what it looks like now. Okay, so you just add a little bit more volume to your ECF. Now let's see what happens if we have high salt intake. What if we just ingested like a bunch of salt tablets? So I'll just write salt tablets. How would it look like then? Well, when you ingest a bunch of salt tablets, that's gonna go to your ECF, all things start in your ECF, and that's gonna increase osmolarity. Increase osmolarity, right? And we have increased osmolarity, it'll draw water towards it osmotically. So fluid will shift over, all right? So you're gonna lose volume from your ICF because it'll shift over. And it'll shift into the ECF, and your ECF will expand in volume. And now it looks like this. All right, so this is the new look of it. That's how it looks like in that situation. How about some other situations? We're just gonna keep going down the list. And there's a picture in my notes that goes through all these situations. I'm just kind of explaining what they are so you're not just memorizing them, okay? So let's redraw it. We have our ICF, ECF. What happens in SI-ADH? SI-ADH, we said, causes euvolemic hyponatremia. So your osmolarity drops and your volume stays the same. You lose osmolarity in your ECF. So now it looks like this. Yeah? And because your ICF has more proteins compared to your ECF, fluid will move towards it osmotically. Move towards it. And dilute it also. So the osmolarity of both sides goes down and you get euvolemic hyponatremia. If it's acute and you retain all that water and your heart doesn't have time to release AMP, BMP to reach that euvolemic state, then you retain that water, right? So it kind of looks like this. In the graph, it'll look like this. Later on, it'll look euvolemic, but this is just how they like to present SI-ADH. SI-ADH. before your compensatory mechanisms kick in. Let's talk about some other ones. ICF, ECF, volume, osmolarity. What happens if you have isotonic loss? Like you bleed out or you have diarrhea that's isotonic. If you just lose water, where does it start? It starts in ECF, so now you lose a little bit of volume. Any changes in your osmolarity? No, it's isotonic. So any fluid shift? No. So it kind of looks like this now. All right, kind of looks like this now. Easy enough to remember. How about adrenal insufficiency? So low aldosterone. What does aldosterone do again? Works on your ENaC channel, takes in sodium, pumps out hydrogen and potassium. If you can't do that, then you can't take in sodium, you pee sodium out, you pee water out, so you lose sodium and water from your ECF. So you lose sodium, so osmolarity will be decreased. You lose water, so volume will be decreased. And because you have so few sodium as compared to your ICF, water will osmotically shift into your ICF. And now it looks kind of like this. And it will increase the volume of your ICF. So now it looks kind of like this. That's adrenal insufficiency. So that's decreased aldosterone, or that's hypertonic loss. You're losing sodium, you're losing water. How about hypotonic loss? So in hypotonic loss, you lose more fluid than salt. The main problem is you're losing way too much fluid. If you lose fluid, well, it'll start in your ECF, so you'll decrease volume. And if you're losing too much fluid, then it'll kind of concentrate any salt you have in your body. Your osmolarity will increase. Osmolarity will increase. Now, what does that do when you have a ton of salt in your ECF? That draws water towards it osmotically from your ICF. So water will shift towards it and leave the ICF. Now it looks kind of like this. That's your new fluid balance chart. All right, so I just went through some situations, kind of explained it. That way, when you're looking at all those different charts, you kind of know what's going on. So rule number one, things start in the ECF. Rule number two, if there's some sort of osmotic changes, then it will cause the water from the ICF to shift. All right, that's it. That's all you need to know. Hope you enjoyed the video. Hope it clarifies some things. Thanks.